recording before I forget. Okay. Test one's just around the corner, but we've got a little bit to finish this week. We're gonna keep working through the normal distribution today, and then I'm hoping we'll have time to start the binomial distribution today, but if not, we'll just kind of I'll adjust the test one content based off of what we're able to finish on Friday. So kind of up to and including end of Friday. I'll post a review, a test one review for the test, so that you can see kind of the breadth of questions that you're expected to be able to do. So it will be longer than the actual test, but the practice for the test will have an outline of what grade distribution to expect for each of the chapters we've done so far, or each of the topics rather. There's definitely going to be some normal distribution stuff on there. And so I just snagged this because we wrote this little summary last day, but so we have, and did you guys both have this table? So last day we kind of learned the rules of the road for the normal distribution, right? And we kind of talked about why we need the z-score. So a z-score helps us find probabilities, so areas under the curve, but it also standardizes values, okay? And so from any normal distribution, we can find probabilities by standardizing our values first. And so we have this kind of chain situation where I have some observation X from some normal distribution with a mean mu and a standard deviation sigma. Okay. We're going to standardize that value. Okay. That value is going to become a lower X because it came from a distribution of capital X. That doesn't matter, but just to explain the different notations. And then we calculate Z. Now Z, to kind of clarify or remind you, right? Z is the number of standard deviations that X is from mu. The number of, I guess I can, the number of standard deviations X is from mu. And we said, okay, kind of convenient that we'll get negative z-scores if it's below the mean, and we'll get positive z-scores if it's above the mean. And Z is, just as a rule, let's do green maybe. Z follows a normal distribution centered on 0 with a standard deviation of 1. And we write that with the shorthand notation that we established, right? Follows a normal distribution centered on 0 with a standard deviation of 1. And so that brings us down from any normal distribution, just kind of shrinks it down, standardizes it. And now we're able to talk about how many standard deviations we are from the mean. Then from Z, right, we can use the Z table. So in class, we're going to use the Z table. But of course, in life, you would use software, Excel, or some other software. There's online calculators and things like that that you can use. Okay. And so, but for in class and for the assignments, you're going to use the Z table unless it tells you to use Excel, right? So, and you've got an Excel assignment showing you how to do it. Right? And so Z is kind of your middleman, right? And then we can use the Z table to find probabilities, right? And the Z table always gives us area to the left, right? But if we want the areas to the right, we do the 1 minus trick, right? We use the total area as 1. We know that that's a fact. Okay. And remember, probabilities are area under the curve. Under the curve. For example, we have 0. The probability of being less than 0 must be 0.5. Just because it's centered on 0 and it's symmetric and the total area is 1, which means that this area must be 1 minus 0.5, which is 0.5. So you don't even need the Z table. If your Z is 0, you know the area to the left and the area to the right, right? It's any other areas that we need the Z table for, because it's it gets difficult when we have this curvature, right? If these were just blocks, we could figure out, we could just add up the areas of the blocks, but these don't behave like blocks, right? And so that's why we need to be careful. Okay, so later today, or I guess in just a blink of an eye, we're gonna go. So for these questions, I give you some observation, and the goal is to find a probability, right? And so we need to calculate Z, and then I can find the probability. This is just the same kind of linkage that I've shown up above, but just briefer, right? And so to get from an X to a Z, you calculate Z as X minus mu over sigma. And to get from a Z to a probability, you use the Z table, which is the one you have, right? And I'll bring fresh copies for the test, so don't worry. Don't you worry. So then we can also move in the other direction. I kind of foreshadowed that last day, but we could start with a probability, right? But then we just kind of work backwards. You still use the Z table, but you use it in reverse, right? That's tricky to think about now because we haven't really done any questions. We've got one lined up, but we haven't really done any practice kind of moving in this direction, but just so you're aware that we can move in the other direction as well. So we use the Z table in reverse, then you get a Z, then you can use this, the Z that you found as your Z here and solve for X, and then you're back to X, right? So it's kind of this, this chain that you can use. And everyone wants to skip the Z, but you can see it's kind of critical, right? Kind of need it. Okay, so then I had this question. I said, try this question for Wednesday, and here we are. Delete. I guess I should change it to, what is it, French's? I'm supposed to buy French's now. Luckily, I don't buy ketchup that often. So at French's Ketchup Factory, doesn't matter, the amounts which go into bottles of ketchup are supposed to be normally distributed with a mean of 36 ounces and a standard deviation of 0.11 ounces. We understand that if you're looking at, you're in the store and you're standing in front of all these ketchup bottles, you understand that the amount that's listed on the label is not exactly the amount, right? There's variability in there, right? And so there's spread in the amount, but there's also some amount that you would think, oh, score, it's so full, right? And so that would be bad for the manufacturer, right? They're putting more product in there than they should be, right? Or than they have to, rather. And then if you get one that's kind of lower, way lower than the other ones, you would say, hey, that's rude. I'm not buying that one, right? because I'm paying for a certain amount and this is less, right? And so that can happen, but they have quality control to handle that, of course, but it can still happen. But we know that the amounts of ketchup in each bottle is going to vary, right? In fact, we're told, uh-oh. I always forget to mute everyone. Okay. We're told that the weights or the, yeah, is it the weights? The amounts follow a normal distribution, right? They're supposed to be normally distributed. That gives me the shape. With a mean of 36 ounces, that gives me the center, and a standard deviation of 0.11. Like we established last day, there's no natural spot to put your standard deviation or your sigma. It's just, we need it for our calculation. So I like to kind of sneak it somewhere below the mean, just kind of make a note of it. Okay. So now we know the distribution of these amounts, right? The amounts of ketchup. And we also know from last day that technically, or I guess in theory, these tails keep going to negative infinity and positive infinity, right? There are physical limitations on our bottle, but in theory, we keep going to negative infinity and positive infinity. The hallway is so loud today, right? It's crazy.
That's what I describe it as being at the airport.
In the E building, I find the air in the hallways really loud. Here, it's just like people passing by. It's crazy. I know the air is loud. Ugh. But it is. If you pay attention in the E building, it's like. Should I do it all ASMR style? Once every 30 minutes, a bottle is selected from the production line, seems reasonable, and its contents are noted precisely. If the amount of ketchup in the bottle is below 35.8 ounces, right, that's below the mean, right? Or above 36.2 ounces, that's above the mean, right? Then the bottle fails the quality control inspection. And so usually if you have something that fails the quality control, you stop the production and you kind of adjust your machinery, and there's probably proper procedures for that. But for us, we just need these thresholds. We're going to start by answering what percent of bottles have less than 35.8 ounces of ketchup. Yeah. For these questions, if I tell you that something is normally distributed, right, just start by drawing the graph, right? And so we'll do it again down here, so it's all part of it. But as soon as you see something is normally distributed, you can draw a graph, right? Draw your normal distribution. I'm sure you can make it nicer than mine, but close enough. Centered on 36, and the sigma was 0.11. As long as the units are the same, it doesn't matter, I just drop them. And if you've done any physics or chemistry or even biology, you would say, you do what? Yeah, I know, bad. But for us, it doesn't matter. We'll bring the units back in later. Okay, so what we want to do is what percent of bottles, remembering that the percent is the same as a probability, which is the same as a proportion, right? And so here, this is a probability. And a probability is the area under the curve. So now we want to find the area under the curve that represents whatever it is that we're looking for. And so as our kind of cutoff here, the observation that I'm interested in finding a probability associated with, that's going to be my X is the observation of interest. This down here is a number line, right? And so this is the amount of ketchup in the bottles. And so I'm just going to put 35.8 here. A little bit tricky because usually in the beginning, you want to be so particular about where you put this thing, but we're only drawing the curve so that we can kind of visualize it, right? And look at the area that we want. And so I give myself, I make sure that I put it below the mean, but then I make sure I don't crowd myself too much, right? And we can adjust this spacing later on, okay? But for now, it's just to figure out where would 35.8 go-ish, right? It's below the mean, so I draw it below the mean. And if I want to find the probability or the percent of bottles that have less than 35.8, right? Then I want this area, right? Which if you find yourself kind of solving multiple problems on the same graph, it can get really kind of boggy with shading. And so I tend to just use this arrow instead, but if you want to shade it, that's great. Sometimes I do both. I like to put a little question mark here just to indicate that that's the area that I'm looking for, right? That's my end goal. Okay, what do you know about this area? Already being below the mean, you know it has to be less than 0.5, right? If you wanted to know the percent of bottles that have more than 35.8 ounces of ketchup, then you know it would be more than 0.5, right? Because from the center on either side, you have 0.5, right? And so being on the left of the mean, you would have more than 0.5. And so there are kind of little checks that you can do along the way to make sure that you're on the right track. And probabilities have to be between 0 and 1, right? And so the smallest you could have is 0. Okay. So going back to our kind of chain reaction, right? Here, the X that I'm interested in is 35.8, right? So let's grab this here. From the question, we were told that mu is 36 and sigma was 0.11. So we can calculate Z. So now we standardize this thing, right? You don't need this. I just want to show you where we are in the path, right? Eventually, we're going to end up here. Got a ways to go. It's kind of like a progress bar for your work. So if Z is X minus mu over sigma, then I get a Z of 35.8 minus 36 over 0.11. That tells me how many standard deviations below the mean 35.8 is. If the standard deviations is 0.11. 35.8 minus 36, I get negative 0.2 divided by 0.11. I get a Z of negative 1.818 repeating. we said for using the Z table only has Z to 2 decimal places, right? And so we round to 2 decimal places. Just so I can put that on the same line here. Z is negative 1.82 round to 2 decimal places to match the Z table. I highlight that it's for the Z table because later we're going to use the T table and it has 3 decimal places. And so you just want to match the table that you're working with. But for now, we've only got 2 and we're not going to introduce the T table until after reading break. So you get a little break. Okay. Now, I have a Z that's here. Right? And so now from here, Z is negative 1.82. That tells me that 35.8 is 1.82 standard deviations below the mean. Okay. So now we're going to use the Z table, remembering that the Z table always gives you the area to the left, which in this case is the area that I want. All right. And so now, usually I like to write it out like this. Using the Z table, the area to the left, you can write it out in words. I'm also going to write it out using probability notation, just so you get used to seeing it, but you're more than welcome to just use words. Okay? It's just longer. It's a party. Using the Z table, the area to the left of Z equal to negative 1.82 is, dun, 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 back we go to our table, our Z table. It's been a while. I guess it's been nearly a week. So here we are. We've got Z, right? Negative Z's, first decimal place, well, and the whole number, I guess, and then the second decimal place up here. So negative 1.82. This tells me that the area to the left is 0.0344. And that's the area that I want. Is 0.0344. Or you can write the probability that Z is less than or equal to negative 1.82 is 0.0344. That's shorter, but take some practice. So if you want to write that, that's cool. I'll know what you're talking about, but you can write it in words too. They say the same thing. So then, if probabilities are the same as percentages and proportions, then what percent of bottles have less than 35.8 ounces of ketchup? Well, 3.44% of bottles have less than 35.8 ounces of ketchup. Therefore, 3.44% of bottles have less than 35.8 ounces of ketchup. Nice. Pretty fun. I was like, I don't know if fun is the word. Pretty cool. Because now we took our negative 1.82, we took it to the Z table, and it spits out the probability, right? You might need to do some adjusting here. And I'll underline it with orange so that they match. So, any questions about this one? What percent of bottles pass the quality control inspection? So if they pass the quality control inspection, well, we remember maybe that the distribution was normal, centered on 36 with a standard deviation of 0.11. And then we were told that if it's below 35.8 or above 36.2, okay, then it fails inspection. So here we have 35.8 and 36.2. Here we fail inspection. Yeah. Whereas here in this area, we pass inspection. So that's the area that we want. Yeah. And we saw this last day where we can kind of use the areas however we want, right? As long as we remember the total area is 1, and you can use that. And what's one thing that you could do? You could use the total area as 1. And if this is the area you want, you could find this tail area, lob it off, find this tail area, lob it off, and then you're left with what you want, right? Another thing you could do, right, is you could find the area to the left of this point, right? Not necessarily using 1, and then subtract this tail area, which we conveniently already found, right? And so, wow, surprise, surprise. So there's lots of different ways that you can do it. And just as long as you remember that the overall goal is to find that middle area, then there's no wrong way, as long as you're explaining to me what you're doing. Okay? So we want to find the percent of bottles that pass the quality control inspection. So we know that this area is 0.0344, right? So from earlier, or from the previous question, I'll say, we know this much. 36, sigma 0.11, and we know, I'll do it out a little bit. 35.8. This area was 0.0344. We know that already. Right? And so, and on the test, I'll ask you kind of an area between two values question, but usually I'll have made you find the area for one of them earlier, and then you just need to build on that, right? So don't start the question all from scratch. You can, but it's a little bit more time consuming. So now what we want is we want to find, how about we do this method where we find the area to the left? Because remember, the table gives us the areas to the left. And so that's going to be easier to work with, right? You can do 1 minus the area to the left. That's totally fine. But either way, color should I do? Let's do pink. We want to add, either way, you'll find the same area. 36.2. Now I want to find this area. From 36.2, I want the area to the left of 36.2, which I know is going to be more than 0.5 for sure, because I'm on the other side of the mean. Right? So now the x that I'm interested in is 36.2, right? And so now I can do z, and sometimes if we're working with multiple z's, right, we can put a little subscript on here, 36.2. So the z for 36.2, right, is going to be x minus mu over sigma, which is 36.2 minus 36 over 0.11, which should be rounded to negative 1.82, right? Because they're the same distance from the mean. That's not going to be the case always, but it's highlighting another thing. So 36.2 minus 36 is 0.2 divided by 0.11. And I get a z of 1.818 repeating. So z at 36.2 1.82. That's the same, right? You expect it to be the same because those values were the same distance from the mean, right? So what could you use? You could leverage symmetry and say, okay, well, by symmetry, this tail area must be the same as this tail area, right? It's not something I'm expecting of you now, right? But eventually you'll kind of start to say, oh, well, couldn't I shortcut this, right? If they're the same distance from the mean, then shouldn't this area also be 0.0344 by symmetry? I'm going to assume we're not quite there yet, but if you are, that's great. You can save yourself some work. So now I have a positive z of 1.82. So using the z table, we find the area to the left of z equal to 1.82 is, make sure you're on the positive side of z, and 1.82, I get 0.9656 is 0.9656. Or if you prefer, the probability that z is less than or equal to 1.82 is 0.9656. That's the shorthand notation if you want. So that means that this area, we can replace it with 0.9656. If we do 1 minus 0.9656, I really hope 0.9656. Phew, we get 0.0344. Could have got there by symmetry, but also just knowing the rules of the distribution, right? Total area is 1. So now we want to find this area. The probability that a bottle passes inspection, or what percent of bottles pass the quality control inspection. Therefore, 0.9656 minus 0.0344 is 0.9312, which you could have gotten to, right, by taking 1 minus 0.0344 minus 0.0344, right? You end up in the same place. Or 93.12% of bottles pass inspection. Always show your work for this kind of stuff, right? And so the more that you can show me, the more I can kind of figure out how to give you marks, right? If you don't show me any work and you just tell me the answer and it's wrong, right, then I can't give you any part marks. So the more you tell me, the better it is, right? Especially if you, for some reason, maybe swapped these values, right? Wrote them in the wrong order. That happens a lot. But then you would get a negative value here, and it would kind of bung things up. And so, but as long as you follow through with that error, right, how are you supposed to know that it didn't make sense, right? And so, or that you kind of switch things maybe. And so as long as you show me all the things that you're doing and just kind of explaining like this, right, using the Z table, you're just saying what you're doing, right? I'm going to my Z table now. And that's how I found that this area is 0.9656. Right, so just kind of explain all the things that you're doing, because I'm more concerned about procedure than I am about getting the right answer, right? And so, right, because so many things can go wrong for a lot of these types of questions, right? And so just show all your work, and ideally draw an image of what you are about to solve, right? How you've interpreted the question is really what you're showing me. Nice. Any questions about that one? Oh, and I guess there's an answer on here somewhere. How about that one? So now, like I said, so now we've done kind of 2 problems working from an X to a probability. Now we're going to work from a probability back to an X, right? And show you what that looks like. We'll introduce a new example. Body temperatures of healthy humans are distributed nearly normally. So as soon as you read that, right, you're going to start drawing a normal distribution just to get a feel for all the information that you get, with a mean of 98.2. Okay. 98.2 goes in the center, and a standard deviation of 0.73. Right, so just kind of grab all the information that you get and put it on a graph somewhere. What is the cutoff for the lowest 3% of human body temperatures? And so I'm going to draw this curve out again, right? And so you can draw it as many times as you want. You could have drawn it down here, but I just wanted to, as soon as you see nearly normal, I want you to start drawing a curve, right? Because it will help you eventually, right? Even though it doesn't feel like it now, right? Oh, and I keep forgetting, but in here, in the school, in my little stickers, it's so cute because there's a normal distribution. Whee! Cute, right? Way nicer than mine, but delete. It's got the 68, 95, 99.7 rule on it, which we're getting to, but not quite yet. Okay. So here I can redraw my curve. 0.73. What's the cutoff for the lowest 3% of human body temperatures? So here on this scale, we've got the temperatures, right? And the lowest temperatures would be down here, right? And so now what we're doing is we're forcing this area to be 0.03 or 3%. But the area under the curve is a probability, right? And so we're always going to use the decimal version. But usually we convert back and forth pretty easily. And so let me just give more room here. 3% or 0.03. So we're forcing that area to be 0.03. I keep thinking of stuff to add. There, like that. So now I have the area that I want to force, and I want to figure out, okay, what value, what temperature makes that happen, right? And so if you've got your little chain reaction here, next stop, I'm going to take this probability and map it back to a Z, right? Just using your Z table. I shouldn't say just because it takes a lot of practice, but you're using the Z table in reverse. So now, right, we're going to look for the table entry closest to 0.03. And don't let those zeros make you go cross-eyed, right? There's a lot of kind of decoys on there. And so here, use the Z table to find the table entry, which is all the numbers in the body of the table, the table entry closest to 0.03. And I'll underline the closest. Then map it back to the Z. Then map it back to its corresponding Z. Okay. What do I know? What do I know about this area? It's on the lower end, right? And so it has to be on the negative side of Z, right? And so I'm going to start looking there, and there is rhyme and reason, but it doesn't feel like it in this table. Okay. So what you're going to do is you're just going to kind of cruise around and look for 0.03. Okay, getting close. And it looks like I'm choosing between these two values. Right. You can kind of cruise around some more, but it reads, so because it goes to the 9th or a second decimal place of 9 this way, you're going to read the table and it just kind of picks up over here on the next line up. And then, so it kind of reads this way, and then you go all the way back, pick up there, right? And so there is There is rhyme or reason, it's just how the table's laid out makes it kind of hard to read. So 0.0301 or 0.0294, I'm gonna say 0.0301 is the closest. Because this one is, in my mind, I think of it as being 1 away. Obviously, it's more than, it's not 1, but kind of. Whereas this one is 6 away, right? If that makes sense. So you can use your calculator, right, and try to figure it out. But just pick the closest one. In fact, again, in the test, if you just tell me the table entry closest to 0.03 is 0.0294, that's not right, but okay, follow through with that, right? Just tell me what it is, as long as you understand that you're looking for the table entry closest to 0.03, then this isn't, reading this table isn't really, you know, a skill that I'm testing, we just need it. Okay, so now I'm gonna say, I'll start my sentence here. So using the Z table, the table entry closest to 0.03 is 0.0301, right? Now my next step is, okay, that maps back to a Z of what? And usually I say which corresponds to Z equal to, I know it's negative, but beyond that, I need the table. Negative 1.88. Nice. So now we're here. Now I have a Z, right? I want to find the temperature that is 1.88 standard deviations below the mean, right? That's what this Z is telling me. And so you can use your formula sheet, or you can rearrange the formula that we know and love already. But for finding the cutoff points, I've put it on your formula sheet. Just kind of sneak it in here. Down here. So it has been rearranged for you. You don't need that one. So usually, right, Z is X minus mu over sigma. Just show you how I would do it without that formula, and then beside it, I'll do it with the formula, right? And so versus, so or X is mu plus Z times sigma. It's just rearranged. So I'll start with our go-to formula, right? But now our Z is negative 1.88, and I'm trying to solve it for X. Mu is 98.2 and sigma was 0.73. So now if I take my negative 1.88 times 0.73, I get negative 1.3724 is X minus 98.2. So my X, if I add 98.2 to what I just found, and then I like to have whatever I'm solving for on the left-hand side. So I use the equal sign as kind of a revolving door, right? A is equal to B is the same as B is equal to A. And so now I'm going to add 98.2. And I find that X is 96.8276 degrees Fahrenheit. Or if you prefer the worked out formula, right, then X is going to be mu, which was 98.2, plus a Z of negative 1.88 times 0.73, which is your sigma. Making sure that you multiply those two values first before you subtract it from 98.2. So you get negative 1.88 times 0.73. So this is the same as 98.2 minus 1.3724. Oh, I did minus. Undo. 1.3724. 96.8276 degrees Fahrenheit. However you want to solve it, right? If you're like me, I don't like to have extra formulas, right? If I just need the one, but a lot of people do like to have them worked out already. So then you're going to be careful that you do this multiplication first before you add or subtract it from the mean. So then the temperature that corresponds to the lowest 3% of human body temperatures is going to be 96.8276 degrees Fahrenheit or less, right? Kind of don't have room to write it out, so that's okay. Usually for these, I'm just kind of getting you to the, as long as you get that X, I'm happy. Right. Any questions about that one? Okay. Little typo here. Normally, body temperatures of healthy humans are distributed nearly normally, with mean 98.2 degrees Fahrenheit and standard deviation of 0.73 degrees Fahrenheit. Same layout, right? Same type of problem, but now what's the cutoff for the highest 10% of human body temperatures? So let's see here. The highest 10%, let's map it out. I'll use this area here. Same type of problem, right? It's still a finding the cutoffs or working backwards type of problem is usually how I think of them. 98.2 and sigma is 0.73. The difference is this, right? The highest 10%. That puts us on the upper end, right? For these highest 10%. So this area, I'm going to force to be 10% or 0.10. Couple of different ways you could solve this, right? I think the simplest way is just to recognize that the table only gives you the areas to the left, right? We can find the area to the left, right? That's going to be 1 minus 0.10, which is 0.90. We could do that. What else could you do? And this is a little extreme, I guess. At some negative z, if we force this area to be 0.10, by symmetry, the z that I'm looking for has to be the positive version of it, right? Because I can take it and I can flop it over to the other side. Right, a little extreme. Let's do both. Right, that z is going to be the same. So first, let's start off with this method here, right, to find our z. I'll try to use some sort of color coordination. Okay, using the Z table, we find the table entry closest to 0.9. To 0.90 is, let's see. Where's 0.90 going to be? It's going to be on the positive end, right? Because it's above. Won't let me erase. So now I'm cruising around these table entries, looking for 0.9, getting close. Okay. Well, now I lost it. Closest I can get is I'm choosing between 0.8897 and 0.9015. Now, like I said, it's not real math, but this one is 3 away and the other one is 15 away, right? And so I'm going to choose this one. 0.8897. Or sorry, 0.8997. Reading is hard. Okay, 0.8997. Let's jot that down. Okay. Is 0.8997, which corresponds to Z equal to, let's see. What's funny about doing these problems is you've probably already done it, and me explaining it takes forever. I get a Z of 1.28. 1.28. Z is 1.28. Oops. Great. That's a positive Z. That checks out with what I wanted, right? Because I'm above the mean, right? And so, okay, that I'm happy with that. Or you could say, using the Z table, we find the table entry closest to 0.10 is, let's do it for some extra practice. 0.10 is going to be on the negative side, and I'm cruising around here. 0.10, 0.10. It looks like I'm choosing between these two values. And one of them is 3 away and one of them is 5 away, if that kind of, or I guess 15 away, bad. Same as before, makes sense. So then I'm gonna go for the 0.1003, but it also corresponds to the same Z, but a negative version, right, by symmetry. So it doesn't matter how you find it. Oh, keep doing that. Using the Z table, we find the table entry closest to 0.10 is 0.1003, which corresponds to Z equal to negative 1.28. So by symmetry, we want Z equal to 1.28. Same result. I'm just showing you the two different ways that you could have done it, right? So whenever there's an or, right, then you've got options. You only have to do one, of course. So now we're back on track. We're able to solve this problem because I have my Z. What's my next thing? I'm gonna find X. And so Z is X minus mu over sigma, and I'm gonna try to keep it on the slide here. Z is, oops, sorry. We already decided it should be 1.28. And X is the value I'm trying to solve for, minus 98.2 divided by 0.73. And I get 1.28 times 0.73 and then plus 98.2. I get a 99.1344 degrees Fahrenheit. Anything beyond that, you're in the top 10% of hottest people. Which is probably not great. I feel like that would be a fever for most. All right. Or in terms of percentiles, you'd be at the 90th percentile, right? Kind of bringing back that terminology. And so let's see here, 99.1344. I'll go with this one. They did some rounding. I want you to keep all these decimal places, right? You don't get a lot, and so you may as well keep them all, show them off. Nice. Questions about that one? No. The 68, 95, 99.7 rule is just a general rule that applies to normal distribution or nearly normally distributed data. Now, we're not going to use this a ton, but this is a good rule of thumb. To estimate probabilities if you don't have a table, right? To estimate probabilities if you don't have a table or software. Pretty rare scenario, right? But it gives us rough approximations. Okay. And there was one year where I taught this entire, it was a different course, but same material with just the 68, 95, 99.7 rule. That's kind of fun. No tables, all right? Just kind of rough approximations. And then of course you would do software to find the exact probabilities. Yeah. We don't get to do that anymore, but it's fun while it lasted. Imagine if you could just have this rule instead of the table. It works the same way though. So for nearly normally distributed data, about 68% of that data falls within one standard deviation of the mean. And that's just a rule of fact, right? And so hence the 68 of the 68, 95, 99.7 rule. Okay. So what that looks like is they've done their best to kind of draw it out, which I always struggle with. And so I'm grateful. But from the mean, if you go down one standard deviation and then up one standard deviation, you've got the central 68% of the curve. Okay. Knowing that, you can find lots of probabilities, right? From here, from the center, one of the things we know is that this area is 0.5, this area is 0.5. The 68 must be split in half, right? And so between 0 up to a standard deviation of 1 must be 68 divided by 2, right? And so knowing these areas and using that symmetry, right, you can find a lot of probabilities. So you wanted to know Gotta straighten that out here. For example, what this probability is. How would you do that? Using just the 68, 95, 99.7. We've only introduced 68 so far. But what's the probability of being less than 1 standard deviation below the mean, is how we would phrase it. Well, I've got 68 in the middle, got a total area of 1, and it's symmetric, right? And so lots of ways I could solve it, but my go-to would be 1 minus 0.68, which is 0.32. And divided by 2, which is 0.16. What if you go to your Z table? What's the area to the left of a Z of what would your Z be here? Z would be -1, -1.00. Let's try it. -1.00. I get 0.1587. Pretty close to 0.16, right? We'd have to get pretty particular. I think it would be something like the 68.2 and the 95.1, and it just gets a little boggy, right? So these are rough approximations, right? And so, but 0.1587, I'd say, is pretty close to 0.16, right? For just a general guide. Okay. So then, probably guessed it already. If you move out 2 standard deviations from the mean in either direction, then you've got the central 95% of the data, right? Or the population. Or the curve. I know, they're all interchangeable. And so 95%, so that's why if we've moved beyond 2 standard deviations, then we consider it kind of unusual, right? Because 95% of our population is within those two bounds. 5% is outside, sure, but 95 is within. And so here, what does that mean? Probability of being less than 2 standard deviations below the mean must be 1 minus 0.95, which leaves 5% or 0.05 divided by 2. So then this area here must be 0.025, which comes from 1 minus 0.95 divided by 2, which is 0.05 divided by 2, which is 0.02. Which makes this area also 0.025 by symmetry. So there's lots of probabilities that we can find. Okay. The tricky part with only using this rule is if you find a Z, let's say you find a Z that's somewhere here, Z is 1.27, just making something up. All you would be able to say if you wanted to know, for example, what's this area, you'd be able to say that it's somewhere between, well, we know this is 0.16 by symmetry and 0.025. That's kind of a wide range. That's why we want to have kind of software or the tables so that we can tighten that up. Right. And so, okay, that area is somewhere between 0.025 and 0.16. Not very helpful, right? And so here, this would be between 0.025 and 0.16. So the tables just help us get a little bit tighter on that, right? Kind of a big range. For our last stop, 99.7% of the curve falls within 3 standard deviations of the mean. We talked about 6 sigma, so the Lean Six Sigma process is really just the 3 standard deviations of the mean. And so, right, you've gone 3 down and 3 up, which is a total of 6 sigma. Okay. And what does that say? 99.7% of your curve falls within 3 standard deviations. Okay. That means that you have 0.3% left over between the 2 tails, right? Very, very, very small. But remember, the tails still keep going to infinity and negative infinity. They keep going, they keep going. There is some probability of these things happening, but it's not very big. So from here, this area is 1 minus 0.997, oops, which is 0.003, and I should divide it by 2, right? Split evenly amongst the tails, 0.0015. And then by symmetry, must be 0.0015 down on the other end. And this stops here, that arrow doesn't, it looks like it keeps going, but it actually just stops there. It's possible for observations to fall 4 or 5 or more standard deviations away from the mean, right? Like I mentioned, there's an assignment question where you're going to be, I think, 13 standard deviations above the mean or below the mean or something. That can happen. It's just very, very unlikely, right? The probability is very, very small, less than 0.0015. Right? That's all we really need to be able to say about that, right? Very, very small. Oh. Nice. So you can find probabilities associated with the 68, 95, 99.7 rule. I always hesitate to introduce it because once you introduce it and once you kind of get it, people only want to use this rule and they don't want to use the table anymore, right? But I want you to use the table. If I want you to use this rule, I would say use the 68, 95, 99.7 rule to solve this problem. Okay. And if you're Googling stuff, this is also called the empirical rule. But if you Google the 68, 95, 99.7 rule, it'll know what you mean. That's the common term for it. So for example, we have that SAT scores, right? And so SAT scores are distributed nearly normally with a mean of 1,500 and a standard deviation of 300, which means if I go from 1,500 and I go down 1 standard deviation and up 1 standard deviation, right? What would that look like? This 1,200 is 1,500 minus 300. And this 1,800 is 1,500 plus 300. So then we would say that roughly 68% of students score between 1,200 and 1,800 on the SATs. I don't know why there's a $sign here. Shouldn't be. Doing the same thing again, but going down another standard deviation and up another standard deviation. This is going to be from 1,500 minus 2 times 300. 1,500 plus 2 times 300. Or just from the previous one, just go down another one, go up another one. And so on and so forth. You can map out, right? The central 68% are between 1,200 and 1,800. the central 95%, right? You have to go out even further, 900 and 2100. And then the central 99.7% of students score between 600 and 2400. Right? I don't know what the maximum is, but presumably it's a little bit higher than 2400. And so there's some probability of reaching that maximum, but it's very, very small. Nice. Oh yeah, any questions about the 68, 95, 99.7 rule? It's not on your formula sheet, so you do have to remember it, but it is in the name. As long as you can kind of attach it to, okay, what does it do? Right. And so, right, from the 68, 95, 99.7 rule, you can find what's the probability of scoring higher than 21% or 2100, for example. You would say, okay, well, that's 2 standard deviations above the mean. And so now that's going to be 1 minus 0.95 divided by 2 because it has to be symmetric, evenly distributed across the mean. And so that's going to be 0.025. So the probability of scoring higher than 2100 is 2.5% or 0.025. You can use those. For these, I went through and I highlighted the correct answer so that we can kind of just focus on the facts, because I do want to talk about why these other ones are true and maybe why this one is false. And I also don't like reading this much, so that's why I highlighted it. Which of the following is false? I also don't like that type of question. You'd think I'd change it, but no, I keep forgetting. I'm going to leave class today and think, I was going to do something. No. Why is A true? Right? This actually requires quite a bit of knowledge about the skew and what happens to the tail, right? So take a moment to think about it. First, we need to know, okay, what does it mean to be right skewed? Let's start there. It might look something like this. Yeah. What happens to the mean in the right skewed distribution? Your mean is going to get pulled in the direction of the tail, right? And so your mean might be somewhere down here. You can still calculate Z scores, right? And Z takes the distance from the mean, right? But now you've got this bulk of data points that are all below the mean, right? And so these would all yield negative Z scores. So negative Z. And this would be positive Z. Right? Depending on which side of the mean you're on. And so then the majority of Z scores in a right skewed distribution are negative. That's true from what we just said. Why is B false? Let's talk about that. In skewed distributions, the Z score of the mean might be different than 0. That can't be, right? Because Z is X minus the mean over sigma, even if it's not normally distributed, right? The Z score of the mean, right? So that means that X is equal to mu. Well, that's the same as mu minus mu over sigma, which is always going to be 0, right? If it is the mean, it has to be 0, right? That's how Z scores work. So that's why it's false. How about C? Oof. Flashback. For a normal distribution, the interquartile range is less than 2 times the standard deviations. Making us work for it. We're told we have a normal distribution. In a normal distribution, the mean and the median are the same, right? So mu is equal to the median. Right? That's a fact for the normal distribution, right? Because they're the same, or it's symmetric. The interquartile range is the distance between the third quartile and the first quartile, but just as a rule, it captures the central 50% of your data, right? And so here, the interquartile range let's tighten it up here. Looks something that's supposed to be even, but right, this is 50%. And this would be Q1 and this would be Q3. Distance between your first quartile and your third quartile is the interquartile range. So now we know that that area is 50%, right? Just by remembering the interquartile range and what it does and what the quartiles do. It's even less than 1 standard deviation away, right? Because if this is the central 50, I can move down 1 standard deviation, definitely at 2, mu minus 2 sigma. Can move up 1 or 2, mu plus 2 sigma. And this area is the 95% by the 68, 95, 99.7 rule. So the interquartile range is less than 2 standard deviations. That's true. That one's worded kind of strangely, right? Should be plus minus 2 standard deviations. It would still be true even if it said within 1 standard deviation. Because then it would be the central 68%, which is still more than 50%. Z-scores are helpful for determining how unusual a data point is compared to the rest of the data in the distribution. That's true. That's pretty much just a fact, right? By standardizing, right, we can compare the number of standard deviations an observation is from the mean. By standardizing, we can compare the number of standard deviations an observation is from the mean. And then, right, we can say, okay, if it's more than 2 standard deviations away from the mean, then we consider it unusual. Right. Values, oh, that should say values. Values more than plus minus 2 standard deviations from the mean are considered unusual. Right. Linking back to the 68, 95, 99.7 rule. Whew. Okay. Any questions? No. We're gonna breeze through the geometric distribution, just briefly. It lays some groundwork for the binomial distribution, which I fear we won't start until Friday, but so the geometric distribution, I'm not going to test you on the geometric distribution. It's just kind of a gateway to the binomial, which I will test you on. Okay. So I will say this here, not on the test. That includes the final exam. If it's not on the test, it's definitely not on the final exam. So we've seen the normal distribution. Now we're going to talk about the geometric distribution. In the geometric distribution, you've actually already solved problems with the geometric distribution. And so questions like, what's the probability that someone who's guessing on a multiple choice test gets the 5th question correct, right? And that's the first one that they get correct. Well, then 1, 2, 3, 4, 5 questions, let's say, right? This one has to be wrong, right? This one has to be wrong, 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 wrong. And then by that condition, this one has to be right, right? And so we know the probability of guessing wrong, assuming there's 4 options, and then the probability of guessing right. You can multiply all those through. Right? And so you've already solved problems like this. But now we'll have kind of a formula that you don't really need. It's not on your formula sheet because it's not on the test. But we are going to refer to this Milgram experiment. And so that's why I have to introduce it. It's kind of cruel, but they got away with a lot. Hopefully they won't say that in years from now. Stanley Milgram, a Yale University psychologist, conducted a series of experiments on obedience to authority starting in 1963. An experimenter, this little guy here, orders the teacher, me I guess, the subject of the experiment, to give severe electric shocks to the learner each time the learner answers a question incorrectly. Right? And so the learner is actually an actor and the electric shocks are not real, okay? But the pre-recorded sound is played each time the teacher administers an electric shock. So effectively the teacher thinks that they're going to shock this person, right? And so they believe that they are. And so now these experiments measured the willingness of study participants to obey an authority figure who instructed them to perform acts that conflicted with their personal conscience. I mean, hopefully, right? You don't want to, you got it wrong. I don't want to do that. No thanks. Milgram found that about 65% of people would obey authority and give such shocks. That's shocking. But over the years, additional research suggested this number is approximately consistent across communities and time, which is, I mean, possibly even more shocking. And so, right, this tells us that the probability of someone kind of obeying authority, even though they probably don't want to, is 0.65. Income Bernoulli random variables. Bernoulli is a famous statistician, and so it's got his name on a lot of things, but each person in Milgram's experiment can be thought of as a trial, right? And so every single time that you try to get either a success or a failure, as we'll introduce, is called a trial. A person is labeled a success if she refuses to administer the shock, and a failure if she administers a shock. Such shock, such shock. From defining our successes and our failures, we can also define the probability of success and the probability of failure. And so here we define a success and failure. But usually the thing we're interested in is a success. I'll add that here. Usually the outcome of interest is a success. Usually it's pretty morbid stuff. If you're trying to find disease data, death data, that kind of thing, then a success is the thing that you're interested in, right? How many people died from this disease? And so then a death would be usually considered a success. You can flip it, but usually it's the thing that you're interested in. Okay. And so I would have flipped these because I guess I'm morbid that way. But we're saying a success is if you didn't administer a shock, right? And so you're allowed to define a success and a failure however you want, right? But that'll determine the probability of success, right? The probability of a success, if a success is that she refuses, right? Then the probability of success is 0.35, which we're going to denote by a lowercase p. When an individual trial has only two possible outcomes, it's called a Bernoulli random variable, right? And so those two possible outcomes are going to be success and failure. Oops. We can usually convert things into a Bernoulli random variable. We can usually create, I'll say success, failure, right? If I'm rolling a six-sided die, right? Then if I'm interested in the probability of rolling a 6, I could say, okay, rolling a 6 is a success, not a 6, failure, right? And so you can do that. You can kind of lump into a success failure a lot of the time, right? So as an example, consider rolling a six-sided die, right? And we want to find the probability of rolling a 6. Then in that case, a success is rolling a 6, and a failure is the complement, not rolling a 6, which is 1, 2, 3, 4, or 5. Right? All of these would be failures, right? And you can just lump them into a failure. So now in this scenario, the probability of a success is 1 in 6. And the probability of failure, is 1 minus p, which I like to use q, a lowercase q, just to save myself a couple of strokes, I guess. 1 minus p instead of 1 minus p, I write q, which I have a note of on your formula sheet later on. But for now, probability of failure, I tend to denote it by a q, but it's 1 minus p, which is in this case 5/6. You thought you were done with that probability section. Almost. Okay. And so going back to the trials, now that we understand kind of success failures, right? Every time the learner answers a question would be considered a trial, right? Because we're just waiting to see, do they give the shock or no, right? Success, failure, success, failure. So every time that you try for a success, whether you get it or not, is called a trial. Here's a scenario. I guess Dr. Smith wants to repeat Milgram's experiments, but she only wants to sample people until she finds someone who will not inflict a severe shock. What's the probability that she stops after the first person? So the probability that the first person refuses is 0.35. What's the probability that she has to stop after the third person, right? So that means that, okay, the first person shocks with a probability of 0.65, right? The second person shocks with a probability of 0.65. And then the third person is going to fail to administer is going to be a failure. No, we're calling it a success, sorry. Not do the shock, refuse, 0.35. So then we can calculate the probability is 0.65 times 0.65 times 0.35, which is roughly 0.1. How about the 10th person? So she only wants to sample people until she finds someone who will not do the shock, right? Who will refuse. So now that means that the 10th person is the first one who says, oh, no thanks. So that means that there's 9 people who did do the shock first, right? And then followed by a refusal. And that's going to look like this, right? 0.65 to the power of 9, right? Or 0.65 times 0.65 times 0.65, blah, 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 times that one refusal that she was aiming for, giving us a probability roughly of 0.0072. The geometric distribution describes the waiting time until a success for independent and identically IID is the shorthand we use, Bernoulli random variables. Okay? You really only need to pay attention to, it's the waiting time until a success. Right? As long as we have these conditions, so the independence, so the outcomes of the trials don't affect each other, right? And so, of course, if I am standing in a waiting room and I'm watching and one of my coworkers refuses to administer the shock, that gives me more confidence to do so, and that would alter my probability of administering the shock, right? And so, so they have to be independent, okay? And identical. The probability of success is the same for each trial, right? And that's one of the assumptions that we make. Going back to these, right, these probability calculations here, right, we have to have, if we're doing n trials, which we'll start kind of incorporating that, right? And so here in n trials, here n is 1. First person refuses, I only do 1 trial. What's the probability that they refuse? Here, n is 3 trials. Here, n is 10 trials. Might be hard to see it for the first one, but if you focus on these next two, right? If n is 3, so 3 trials, then n minus 1 of those have to be failures, right? The probability of a failure. And the last one, right? The nth one has to be a success. And so n minus 1 of these have to be failures followed by a success, right? Which we can communicate as a formula like this. But like I said, you've already solved problems like these. You just didn't have the formula there. I'm trying to zoom in. If P represents the probability of success, then 1 minus P represents the probability of failure, and N represents the number of independent trials. then the probability that you get a success on the nth trial is you have to have n minus 1 failures times 1 success. N minus 1 failures, 1 success. Can we calculate the probability of rolling a 6? I did read through these before class, so it was probably incepted. But anyways, incepted. Rolling a 6 for the first time on the 6th roll of a die using the geometric distribution. Note that what was a success is rolling a 6, and what was a failure, which is not rolling a 6, are clearly defined, and one or the other must happen for each trial, right? You roll a die and you either get a 6 or you don't, right? And they're all independent because those probabilities are independent. So of course, the answer is yes, why not? Kind of a weird answer, but let's do it. Let's find the probability of rolling a 6 for the first time on the 6th roll. For the first time on the 6th roll, wow, is no shorthand here, just the probability notation. I like to do these, right? So now I'm gonna go up to the 6th roll, and so I like to have 1, 2, 3, 4, 5, 6 rolls, right? This is the first time that I get a 6, right? I roll a 6. Here I don't, here I don't, here I don't, here I don't, here I don't. Okay. Probability of not rolling a 6. Let's say P is 1 over 6, and Q, which is 1 minus P, is 5 over 6. So the probability of not rolling a 6 is 5 over 6, 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 and then finally 1 over 6. This is the same as 5 over 6 to the power of 1, 2, 3, 4, 5 times 1 over 6. 5 over 6 to the power of, whoops, not 6, 5. Times 1 divided by 6. I get roughly 0.06697959534, roughly. Nice. I guess I should ask any question. Yeah.
How many decimal places do you want us to keep on?
If this is the end of the part and you don't have to use it again, you can just give me all of them, right? Or at least 4 in this scenario. 4 would kind of capture a lot of activity. In this scenario, I would go to probably round up 7 to 8, right? Kind of make sure you capture as much activity as you can. So I don't really have rules, but usually 4 decimal places is a safe place, right? But if you're carrying it through, you can do kind of 2 or 3 as long as you don't lose a ton of information, right? For these probabilities, if they're very small, I want more decimal places, and if they're kind of, 0.12, then you can kind of round titer. I know, not very helpful, is it? How many people is Dr. Smith expected to test before finding the first one that refuses to administer the shock? The expected value, we've seen the expected value before, it's the mean. And the mean of a geometric distribution, just as a fact, is 1 over p. Yeah. And so 1 over p in this case is 1 over 0.35, which is 2.86. So she's expected to test 2.86 people before finding the first one that refuses to administer the shock. That can't happen, right? She can't test 2.86 people, but we've seen the expected value before, right? We've seen, okay, the expectation, right, is if she did it many, 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 many times over, this 2.86 on average over many repetitions of the experiment. Right? We've seen the expected value before. In fact, we used E of x is equal to mu. Be nice to see that again. There's variability as well for your geometric distribution. These aren't on your formula sheet because I'm not going to ask you questions about it, but it's nice to see that we can calculate the mean and the standard deviation. The standard deviation only uses p, right? And p was the probability of success. So where p is the probability of success. So we can find the mean and we can find the standard deviation just using p, right? And so in this case, if our p is 0.35, our sigma would be 2.3. And so Dr. Smith is expected to test 2.86 people before finding the first one that refuses to administer the shock, give or take 2.3 people, right? All these 0.3s, 0.86, these values only make sense in the context of repeating the experiment many, many times. Right? There. We're going to pick up at the binomial distribution on Friday. You did it. Good job. If you have any questions, let me know. Otherwise, see you Friday. I'll stop this recording though. Please stay on the line.